Hi everyone, it's Mr. Singh here with the next video in the list of revision videos where we break down a question to do with a previous topic. And this time round, we're going to look at the electricity topic. So I've got three questions that you can also download and either print out or have open on another device so that you can work along with me. Of course, you can pause the video, have a go at some of the questions, and then check them along with me and get a bit of an insight into what the science is behind the particular questions that we're going to look at today. So we'll start off with the first one. And this is a question that's kind of quite general, quite broad in its scope. There's a little bit on circuits, but there's also some calculation type questions as well. And calculations and equations is a big part of electricity. So let's take a look at what this question wants from us. So question itself is about an investigation that a student's doing to take a look at how the potential difference across a filament lamp affects the current in that lamp. So this is the circuit that the student is using. If we just go around the circuit clockwise, here we've got a battery made up of at least two cells, because we can see one cell here and one cell there. We can see an ammeter. We can see how this circuit moves around clockwise here to include a filament lamp or a lamp. There's a voltmeter across the lamp. And then moving around the left-hand side to complete the circuit, we have a variable resistor. So we can see that this is a series circuit, albeit the voltmeter is connected in parallel around that lamp. Now, figure 2 zooms in on the component at the top of the circuit. So here we have it isolated and on its own. What does the component represent? Well, like I've already said, this is a battery. It's a battery and not a cell because we have more than one cell. When we connect more than one cell together in series like this with the right orientation, the cells need to be in the same direction or alignment as each other. We have a battery. There's no confusion in the question as to whether we put a battery or a cell, because we can see using the process of elimination that battery is the only viable option. It's obviously not an ammeter, a lamp, or a variable resistor. So it's got to be this answer here. Question B, which component from figure 1 did the student use to adjust the potential difference across the lamp? If we take a look at the circuit again, the only thing that's going to adjust the potential difference across the lamp, so how much energy is transferred at the lamp, is the variable resistor. It's not the battery, because the battery itself will have a fixed potential difference. The ammeter is only there to measure current. The voltmeter is there to measure the potential difference across the lamp. The variable resistor, however, is able to adjust the current that flows through the circuit. So by way of doing that, the amount of energy transferred across the lamp because of the changing current or electrons per second that move through the lamp can be adjusted by changing the variable resistor. So that's the answer to question B. So variable resistor. Moving on to question C. When the voltmeter was not connected to the circuit, it gave a reading of 0.4 volts. So this voltmeter, even when not connected to a circuit, has a reading on it already of 0.4 volts. How can the student correct all the readings taken from the voltmeter? If we have a situation where a measuring device already gives us a reading of whatever it's supposed to inform us about, we call that a zero error. So a device that isn't displaying zero when it's not being used has a zero error. So how can the student correct all readings taken from the voltmeter? Well, if we imagine that this voltmeter is displaying 2.04 volts, or any number that is 0.4 volts, so not 2.04, 2.4 volts, then we can assume that 0.4 volts of this reading shouldn't be there. So the logical thing to do there would be to subtract that zero error. So to take that 0.4 volts away from the displayed reading, meaning that this reading would actually be 2.0 volts. So the answer there is the bottom box, subtract 0.4 from each reading. So 0 error. Part of the skills that you need to have for the exam include identifying 0 errors or errors in general. So we'll look at those in lesson in some more detail. But as far as this one goes, quite a straightforward one. Question D. Student recorded 3 values for current for each potential difference. The table below shows the results for 2.5 volts. So when there was a potential difference of 2.5 volts across that lamp, these are the 3 current readings that the student got. Very straightforward question. Calculate the mean current in the lamp. Now, when you see questions like this, look out for anomalies. Now, as far as we can see here, doesn't seem to be anything that I would call an anomaly. Yes, the 0.58 is a little bit higher than 0.54 or 0.53, but I wouldn't call that an anomaly. Anomaly is something that really sticks out, that looks really different to the pattern that we can see. So what we do here, we add all of these together. So 0.54 plus 0.58 plus 0.53, add them all together and then divide by 3. So doing that, we get 0.55. 0.55 amps is the mean current. Now you can see that they've given these values to 2 decimal places, so we should do the same. So 0.55. Okay, moving on to question E. Calculate the power of the lamp when the potential difference across the lamp was 4.8 volts. Sorry, the current in the lamp was 0.75. Use the equation. So this particular question here provides us with this equation. This is an equation, however, that you do need to learn. So power equals potential difference times current. So in symbol form, P equals V I. So you do need to learn this equation, but here we're given it. So simple case here of substituting the values in. Doesn't look like we need to convert anything because the voltage or the potential difference is in volts, not millivolts or kilovolts. The current in the lamp was 0.75 amps. Again, amps is the standard unit. So put those numbers in. So the power equals 4.8 times 0.75. Doing that, we get an answer of 6.4 watts. Unit's already there for us. The unit of power is the watt. Again, need to know that as well. But in this case, that's printed for us there. So hopefully a nice, easy 2 marks. Turning over. Again, another equation here, another calculation. I chose this question specifically so that we could revisit these equations. This equation again is one that you need to learn, the one that you need to remember. This time we're being asked to calculate the resistance of the lamp when the potential difference across the lamp was 4.8 volts. So we've got the same voltage or potential difference from the previous question. Calculate the resistance. The current is 0.75 amps. Use the equation. Again, we're given the equation here. Chose these questions so that we could see these equations. I'll write down the symbol form here for you so that you've got at a glance the equation that you need to learn in symbol form. So resistance is R. Resistance equals potential difference, which is V over I. Commonly, you see this equation written out like this, V equals I R. That's the way in which you taught it, although these are just rearranged versions of the same equation. But again, you need to learn this equation. So substituting the values in again in this question here. Hopefully you've already done this. If not, that's fine. But having a go at these questions before, seeing what you got and seeing how they compare to my answers will be a good way of testing yourself. So R equals 4.8 divided by 0.75. That equals 6.4 ohms. What I've just realized is I've actually done the previous question incorrectly, because rather than use the calculator, I looked at the mark scheme, I looked at the wrong answer. The answer to this question was 3.6 watts. Hopefully you didn't have to mare like me, but make sure that you go back and check that. Make sure that you're actually doing your working out and not just mindlessly writing down wrong answers like me. Yeah, so this one is 6.4 ohms. Ohms is the unit for resistance. And then moving on to the last part overall of this particular question. Complete the sentence, choose answers from the box. You can use each answer once, more than once, or not at all. Might seem like don't necessarily need to go into this, but this is a really important command here. You know, sometimes we think that we might be able to use only one of these answers only once, but we do have the option to use them once, more than once, or not at all. So the words are decrease, increase, and stay the same. Increasing the current in a filament lamp makes the temperature of the lamp do what? Well, passing more current through any component, really, a wire or a lamp, is going to increase the temperature. And the reason for that is that the current, which is obviously made up of electrons traveling through the component or a wire, that's what current is. It's the rate of flow of charged particles, causes collisions. So you've got, for example, a wire like this, and you have ions in the wire. I'm drawing positive charges in these like that. And then you've got these electrons. Now, the current is the flow of these electrons through the conductor. Now, every now and again, these electrons will collide with the metal ions and they will transfer energy to those ions in the form of kinetic energy. That causes these to start vibrating, and that in turn increases the temperature of the material that the conductor is made of. So the greater the current, the greater the temperature, or the greater the rise in temperature of that conductor will be. If these ions, or whatever this conductor is made of, start to vibrate more and the temperature increases, and again, that in turn causes the particles to vibrate more, then it's actually going to be even harder for these electrons to flow through from the beginning to the end of the conductor. Now, when that happens, what we say is that the resistance has increased. So the greater the resistance, the less current can flow through. So if it's difficult for these electrons to flow through because these particles are all vibrating, then we say the resistance of the lamp or the conductor has also, therefore, in the case of this question, increased. That links nicely on to the next part of the question, the final part of the question, in which we can see these current voltage characteristic graphs. These are graphs that give us the behavior and the characteristics of the current and the potential difference of three different components. And you need to know what these are. I'll tell you what they all are after you've had taken a look at the question. So which graph shows the relationship between potential difference and current for a filament lamp? So this is something that you actually not only need to know, but you not only need to be able to identify, is you actually need to be able to explain. Now, going in with the answer, first of all, this is the answer to the question. A filament lamp has this characteristic shape. If we take a look at the center of the graph, so the origin point of the graph, we can see that as we increase the potential difference, the current also increases. So we, for some part of the graph at least, have what looks a little bit like a directly proportional relationship. But then later on, we see that as the potential difference increases further, the current actually starts to trail off. It starts to level off. It's because at this point of the graph here, where we're at this higher potential difference, there are a lot more collisions. There's a lot more heating of the filament within the lamp. And that means that the resistance of the lamp actually starts to increase at this point here. If the resistance is increasing, it's more difficult for the current to flow, and therefore the current doesn't increase as much as we get to this part of the graph. You can see exactly the same pattern here for the negative potential difference values. The only difference really here is that at negative potential difference values, the current is flowing in the opposite direction. So it's still the same pattern, but it's just happening in the opposite direction. This particular graph here is the current voltage characteristic graph for a fixed resistor. Fixed resistors show a directly proportional relationship with no change in the current as the potential difference rises. And then this one over here is for a diode. And for a diode, we can see that as we increase the potential difference for at least a small part of the graph, at the lowest potential differences, we get no rise in current. And we reach a certain voltage over here where the current starts to flow. Negative potential differences, though, provide no current whatsoever because diodes only allow current to flow in one direction. So in this case, in this section of the graph where the potential difference is negative, we actually get no current whatsoever, regardless of the value for that potential difference. Whereas on this side, after a certain potential difference, we do get current. Okay, so moving on to the next question, which I've chosen as it links to the theme of domestic electricity, so electricity that's supplied to homes, and also some of the safety aspects of that particular area of electricity. So got a plug here that's opened up to show us what's going on inside. Diagram shows the inside of a plug, and then we've got some of the wiring that's going on in there as well. Rather than talk you through all of the different parts, what I'll do is I'll jump into the questions and then use some of the ideas that come up in each of these questions to actually deconstruct that diagram. So first of all, we're told that the plug is not wired correctly. So we need to take a look at this diagram to see what's wrong. What should be done to connect the wires in the plug correctly? Well, one of the things that you need to learn, or three of the things you need to learn, are that there are three cables, three wires within a plug that we use to supply appliances in the home, school, whatever, with electricity. So we have we'll go around clockwise. We have an overall cable that contains a green and yellow wire, a blue wire, and a brown wire. Now, just referring to what each of these is actually called, the green and yellow wire is known as the earth wire, and that connects to the earth pin. And you can already see that the green and yellow wire, which we're calling the earth wire, is actually not connected to the earth pin, which is up here. It's actually connected to the neutral pin. So moving around to the next wire, the blue wire, well, the blue wire is actually called the neutral wire. So I guess we figured it out then. We figured out the problem. These two wires seem to be switched. They seem to be crossed. Just going around to the final wire, the brown wire, this is known as the live wire. And as we can see here, as it emerges from this cable, this insulation here, it actually connects to the live pin. So as far as this plug is concerned, the live wire is connected to the live pin, which means that that's really the only part of the plug at the moment that is correctly wired up. So we can see that the green and yellow wire, which is the earth wire, is connected to the neutral pin, whereas it should be connected to the earth pin. And the blue wire, which is known as the neutral pin, is connected to the earth pin, and it should actually be connected to the neutral pin. So, simple answer to this question, we just swap the blue wire with the green and yellow wire. You can say that in different ways. You could actually name them, okay? You could say swap the earth and neutral wires. You could also say allow, so to connect the blue wire to the neutral pin and the yellow and green wire to the earth pin. So just need to get the message across that those two wires are going to need to be swapped. Okay, so the correctly wired plug and cable connects to a washing machine to the mains electricity supply. Give the potential difference in the frequency of mains electricity supply in the UK. So these are just facts that you need to know. So the potential difference that's provided by the mains electricity supply in the UK is 230 volts. So that's something that you need to know. So just like the cells or batteries that you might have inside a TV remote or any other kind of device that uses batteries, they generally provide something in the region of 1.5 volts. So mains electricity provides a much higher potential difference. So it's therefore able to transfer a lot more energy to the devices, which makes sense because usually, things we plug into the mains electricity are quite powerful in terms of the energy that they can transfer. The frequency, which is essentially as mains electricity provides AC electricity, so alternating current, is just the rate at which the electrons, because this is what alternating current is, the electrons move forwards and backwards. The frequency is just the rate at which they move forwards and backwards. And in the UK, the frequency of the mains electricity, the frequency of the AC electricity is 50 hertz. 50 hertz. Okay. Question C, the washing machine is switched on. What is the potential difference between the neutral wire and the earth wire? Okay, so the neutral wire and the earth wire aren't actually connected with each other or to each other in a device that's working or operating normally. So for that reason, the potential difference between those two cables, those two wires, should be 0 volts. What we actually should have happening is, if we just represent the device with this box, is we should have, I'm just going to draw the earth, well, I won't be drawing the earth wire. I'm going to draw the live wire as this red wire, like this, which connects to the device, and then the blue wire, which connects to the device and takes the current back to the main supply. Is we should actually have these two wires. So the live wire, if you like, bringing the current in, and the blue wire allowing a connection back to the mains. Now the live wire has a potential difference of 230 volts, and the earth wire has a potential difference of 0 volts. So the potential difference between these two wires is 230 volts. The earth wire is actually connected to the casing of the device, and under normal operating circumstances shouldn't actually be carrying any current at all. So it's also at 0 volts. So what you can see here is the neutral wire and the earth wire both have a potential difference of 0 volts, which means that the potential difference between them is also 0 volts. The earth wire only carries current when there is something wrong, when there is some damage to the appliance. And that's what we're going to take a look at in the rest of this question. Question D, the plug has a fuse. Draw the circuit symbol for a fuse in the space below. So you can see the fuse right there. Circuit diagram for a fuse looks like this. So it's a rectangle and then a lead or wire that runs all the way through. So in a fuse, the lead, the wire that's within the fuse, has a particular melting point, so a particular current that flows through that wire. If that current is exceeded, then this filament, this small thin wire, high resistance wire in this fuse will melt, and that will create a break in the circuit, preventing any current, any electricity from flowing to the device and potentially saving you from a fire. So the washing machine has a metal case. A fault causes the live wire to make an electrical connection with the metal case of the washing machine. The earth wire is not connected to the metal case of this washing machine. Explain why it would not be safe for a person to touch the metal case. Okay, if we use my amazing diagram here to kind of represent what's going on, essentially, what's happening in this question is, I'm going to draw the individual wires separately as opposed to within installation. Is we've got this live wire like this, which should be running to, I guess, the motor inside this washing machine. It actually comes loose and it makes contact with the casing. Okay, we do have the neutral wire that's connected up to the motor, but essentially this live wire and this neutral wire are now no longer part of the same circuit because the live wire has come loose. So if the person was to touch the casing of this washing machine now, there really is nothing other than the following that could happen. So we've got this current that's flowing through the live wire. This current will now flow through the casing of the washing machine, represented by this yellow pen here, into the person and straight down to the ground. And as that happens, this person is going to be suffering from a massive electrical shock or electric shock. In other words, they're going to be electrocuted. And that's because the current is actually able to flow through the person. So got quite a lot of space for this question, but really it comes down to 2 points. It is worth 2 marks after all. Firstly, the person is going to get an electric shock. That is why it is not safe. Secondly, the reason for that is that current flows through them. because the person provides a connection from the washing machine down to earth. There's a potential difference across the person. That means that the current can flow through that person, and that's not going to be very safe at all. Okay, in the next part of the question, it states now that the earth wire is connected to the metal case of the washing machine, and explain why it would now be safe for a person to touch the metal case, even if the live wire is still touching the metal case. So for this, let's draw the third wire. So I'm going to draw my green wire, which is representing my live wire, and this is actually bolted to the case of the washing machine. Now, you're going to have to ignore the yellow wire now. I'm going to switch over to orange to make it look different. This washing machine is still not going to work properly because the live wire is no longer connected to the motor, which is what's going to cause the whatever you call it, the chamber, the drum, or whatever, to spin. So now what we've got is the current flowing through our live wire like this, still going through the case, around the top over here. Now, at this point, where the person is actually touching the case, the current is not going to flow through them. And the reason for that is I'm going to tell you a phrase now, is that current or electricity always takes the path of least resistance. Now, compared to this nice copper earth wire, the person has a much higher resistance. So rather than go through them, the current actually travels towards where the earth wire is connected, through the earth wire, straight back down through the pin, and then straight down into the earth, which there'll be connection between all of the main sockets and electrical inlets and outlets of the house, straight down into the ground. So this person now does not get a shock. Now, again, it's worth 2 marks. It comes down to 2 main points. So this time, it's now safe for the person to touch because the charge or current flows through the earth wire instead. And the reason for that is that the earth wire has a much lower resistance. Okay, there you have it. We're at about 27 minutes now, so I am going to cut this video here. If you have any questions, obviously, as usual, get in contact with your science teacher or see myself, or send an email through. There is another question for you to have a go at in the pack of questions that are attached in the description of this video. So feel free to complete that video. And again, if you have any questions about it, please ask your science teacher. Until the next time, see you later.